see here the amount of energy released, it is called as the lattice energy. Then next you have to go through the overall energy change of the reaction, that is Na plus half Cl2 giving NaCl. So here the energy involved or the enthalpy change, there it is the delta HF, that is the enthalpy of formation. Okay, that means one sodium atom, it will be combining with half of the chlorine molecule to form sodium chloride crystal. Then you have to see what is Hess's law. So Hess's law means Hess's law states that it is the overall energy change depends only on the initial as well as the final stages of the reaction. That means it does not depends upon the steps involved in that particular reaction. Okay, so the Hess's law states that the overall energy change in a chemical reaction, it depends only on the initial as well as the final stages. So from this, assuming this Hess's law, we can write the equation as delta HF, that means the enthalpy of formation. Okay, it will be equal to delta HS. That means delta HS, it is the energy or the enthalpy of sublimation that is involved in the first step, isn't it? So delta HS plus in the next step chlorine molecule, it is converted to gaseous chlorine atom, that is the delta HD, dissociation energy. Okay, then in the next step the energy involved is ionization energy to convert gaseous sodium to sodium ion, and in the fourth step it is the electron affinity, and in the fifth step the energy involved, that is the lattice energy. So you have to sum all these terms to get the total energy change or the overall energy change. So we can write it as delta HF is equal to delta HS plus half into delta HD plus ionization energy plus electron affinity plus lattice energy U. Okay, so here the ionization energy, again this delta HS, you have got some values for this for the sodium chloride crystal formation. Okay, that means the enthalpy of sublimation in the first step, the energy change involved there is 108.4. Then delta HD, the dissociation energy, it will be equal to 241.8 kilojoule per mole for chlorine molecule. So here you have to take half of this value. And again the ionization enthalpy of sodium ion, that is equal to 495.4 kilojoule per mole ionization enthalpy. Then comes the electron gain enthalpy or the electron affinity, that is equal to minus 348.6 kilojoule per mole electron affinity. And the last one, the overall energy change, delta HF is equal to minus 381.2 kilojoule per mole. Okay, so these are the values there. Then you have to substitute these values in this equation. So by substituting these values, you can calculate which one? The lattice energy. Okay, all other values you know, delta HF you know, delta HS, delta HD, ionization enthalpy, then electron affinity. So all these values are here. So you have to substitute and then calculate the value for U. Okay, so therefore we can calculate the lattice enthalpy, the lattice energy of this sodium chloride crystal. So the lattice energy U is equal to the value will be, I am not writing the whole substitution etc. So it will be equal to minus 757.3 kilojoule per mole. Okay, so the lattice energy involved in the formation of formation of sodium chloride crystal, that is equal to minus 757.3 kilojoule per mole. You have to do this simplification, substitute these values. Okay, for delta HF, that is delta HF minus 381.2, that is equal to delta HS is equal to 108.4 plus half into delta HD, that is half into 241.8 plus ionization enthalpy, that is 495.4 plus electron affinity is minus 348.6 plus lattice energy. Then you have to simplify. Okay, so while simplifying you will be having the value minus 757.3 kilojoule per mole. Okay, so this is regarding the Born-Haber cycle as well as Hess's law. Both are important and you have to study this by heart. It will be asked for a 4-mark question usually. Please go through this also. Okay, then the next one, see I am skipping one small topic, that is the solvation energy, that I will take you in your next session. Okay, next is the partial covalent character of ionic bond. This is another important topic. Partial covalent character of ionic bond. That means how an ionic bond shows a partial covalent character. Ionic bond means it is usually polarized bond, isn't it? It has got plus or minus charges. Then how it will be having this covalent character. That is what is explaining here. That means, see here, when two ions, when a cation, this is a cation, say A plus. In your textbook it is given as A plus, and this is an anion, B minus. Usually these cations will be smaller in size and the anions will be bigger in size, isn't it? So when these two are brought together to a closer distance, what happens? See here, there will be some interactions between these two, isn't it? See here, the first ion, it has got a nucleus, and the second ion, it has got a nucleus, isn't it? So what happens is that this cation, it will be attracting the electrons on the anion, isn't it? See, electrons are here, electrons are revolving here. So this cation, it will be attracting the electrons on the anion, and at the same time, see, what about the charge of the nucleus? Nucleus has got a positive charge. So here this will be having an attractive force. At the same time, there will be a repulsion between the nucleus, isn't it? That means both attraction will be there. At the same time, repulsion will also be there. Repulsion between the nucleus will be there, isn't it? So as this happens, what happens? There will be a distortion or polarization will be happening to this negative ion, isn't it? Some attraction force is there, at the same time some repulsion is there, and as a result some distortion or some polarization will be there for this negative ion. Okay, distortion or polarization occurs for the anion. And usually, see here, similarly the negative ion will also will be polarizing this positive ion. Okay, just the reverse will be taking place. And also see, usually what happens, the size of the anions, while comparing the size of the anions and cations, anions are much more bigger, somewhat bigger while comparing with the cations, isn't it? So what happens is that the effect of a larger ion on a smaller ion will not be much high. That means the effect of a larger ion will be larger ion on a smaller ion. The effect of larger ion on a smaller ion will not be much high. It will be very less. But that means the degree of polarization, will be small, isn't it? The degree of polarization will be small. If the degree of polarization is small, that means the bond will be remaining ionic. Okay, the bond will be ionic. But see, if the degree of polarization is high, then what happens? The electrons, it will be moved towards the electrons will be moving towards the positive ion, isn't it? The electrons in the negative ion will be moving towards the positive ion. So as a result, what happens? The electron density between the two nuclei will be increasing, isn't it? So in the anion, some electrons are there. If the polarization is large, what happens? These electrons will be attracted towards the positive ion, and as a result, see here, in between the two nucleus, the concentration of the electrons or the electron density will be high. Okay. So as a result of this high electron density, what happens? A degree of, here the electron density high means the covalent character will be increased. So we can say that if the polarization is high, what happens? The degree of covalent character will also be there. Okay, that means a covalent character will be developed in between an ionic bond if the degree of polarization is high. If the degree of polarization is small, what happens? The bond will be ionic in nature, and if the degree of polarization is high, the bond will be covalent in nature. Okay, so here see, we can see there is a transition from ionic to covalent character, isn't it? A transition from ionic to covalent nature occurs, covalent character occurs, and this transition, it is governed by a rule called as the Fajans rules. Okay, so this is also very important, Fajans rule. Okay, so here this the rule governing the transition from an ionic to covalent nature, it is called as the Fajans rule. So we have to go through some of the points of this Fajans rule, and the first point is that see here, this Fajans rule, it is regarding the polarization. Okay, Fajans rules deals with the polarization. So the first point is that a small positive ion favors covalency. A small positive ion favors covalency. A small positive ion favors covalency. See here, that means small positive ion means, see here, the ionic size will be very small and the positive charge, it will be concentrated at this small volume, isn't it? The positive charge, it is much concentrated in a smaller volume. So that means smaller volume, the concentration is high. That means it has got a high charge density, isn't it? It has got a high charge density. And as a result of the high charge density, what happens? It will be becoming highly polarizing, or the degree of polarization will be high. I am writing it as dP in short form. Don't write like that. That means the degree of polarization is high. So that is the first point. A small positive ion favors covalency. Then the second point is that a large negative ion favors covalency. A large negative ion favors covalency. So here also larger ions means they are highly polarizable, isn't it? The size will be high. That means the electron density is not so much concentrated, isn't it? So what happens is that when a positive ion is comes near to this one, what happens? It will be much distorted to the electron cloud will be much distorted to the positive ion. Okay. So this electron cloud will be moving away from the nucleus. Also see, since it is a bigger ion, the attraction between the nucleus and the outermost electrons will not be so high. So while a positive ion is attacking towards this negative larger anion, what happens? The electron clouds will be moving towards the smaller cation. So as a result, a covalency. So here an electron density will be increased, and as a result, a covalency will be developed here. Okay. So that is the second point. A large negative ion favors covalency. Then the third point is that larger charges on both ions favors covalency. Okay. Larger charges on both ions favors covalence. That means if it can for a positive ion or it can be for a negative ion, either for both the ions or for each of these ions. Okay. So larger charges will be favoring this covalency. That means if the charges are 3 plus or 2 plus like that, the covalency will be more favorable. That means highly charged anions are easily polarizable. Then the last point is that if the ions, if it is having a noble gas configuration, the covalency is not favored. Okay. So if the positive ion does not have a noble gas configuration, the positive ion does not have a noble gas configuration, what happens? What happens to the polarization if it is not having a noble gas configuration? Noble gas configuration means it is an inert gas configuration, highly stable. So if it is not having the noble gas configuration, the polarization will be high. Okay. Polarization will be high. If the polarization is high, then what happens to the covalency? Covalency will also be high. Okay. So this is the last point, polarization. If it is not having a noble gas configuration, the polarization will be high. Okay, so in the next class, we can go through the partial ionic character of the covalent bond. So you have to study all these things. Fajan's rule is very important, and also the partial covalent character of the ionic bond. Again, the reverse is there. That is the partial ionic character of the covalent bond is also there. That portion we can see in our next session. Okay, thank you.